So we're going to be taking a look at question 3 on the review guide. So Sydney's walking at 2 meters per second for 39 meters, and then she sees her friend Lily, who was another 16 meters away, so she started running at 3 meters per second squared to catch up to her. Let's go ahead and take a look at how to attack this problem. So in the diagram here, we would expect that we would actually have two different velocities. All right, one velocity at 2 meters a second, the other velocity at 3 meters per second. So I'm going to go ahead and break this up into two sections. And in the first section, it looks like we are not going super fast, right? 2 meters per second. So we're not covering a whole lot of distance. So I would have my hash marks or my dots, however you want to draw this, close together. Right, because each one of these, we're not traveling a lot of distance. For my second part of our motion here, we'd be at 3 meters per second. I don't have to draw this in scale in relation from 2 meters per second to 3 meters per second. I don't have to draw that it's 39 meters or 16 meters or anything like that. All I'm doing is I'm showing that we were going slow, and now we're going faster. Right, we're covering more distance here, here, and here than what we were before over there. All right, if you wanted to, you could label this first part as being 39 meters, this second part as being 16. Again, it doesn't have to be to scale. I know mine's not, but even if you just wrote it exactly like what I have there, you'd be good to go. All right, so the graphs, we haven't done graphs in class like this one before, but you have the knowledge to be able to do this. Right? So it looks like, to begin with, I have a constant velocity here. Right? So my distance, it's going to be increasing at the same rate throughout this first half of my path of travel. So I would expect to go from 0 and get further and further and further away from 0, but I'm going to have a shallow slope, right? Because I'm not really going that fast. But then the second part here looks like I'm going to have a steeper slope because my distance between each of my hash marks is further, right? So that means that we're going faster. So I would expect to start from here. Now, normally we would have a curve, but in this case, it's actually going to be a flat line, right? Because, again, my displacement is changing at the same rate because this velocity that we have up here is changing at the same rate. Actually, I should say it's not changing at all, right? Our velocity is staying the same for that second part. So here it does tell us to ignore any acceleration, which is kind of weird because you're like, well, wait a second, aren't we accelerating? We're going from one velocity to another. Yeah, but we're assuming this is instant. It's not a gradual acceleration, which is why we don't have a curve here. All right, so then for my velocity, well, what does that mean? Well, this first part here, we're going at some sort of meters per second. We're actually going 2 meters per second. This second part here, we're going 3 meters per second, which means I'm getting faster. But if I'm going 2 meters per second the entire time for this first half, that means that my velocity is going to be constant. And then for the second half here, it's going to be a faster velocity. Right? And again, we don't have the numbers, so we don't know exactly where to place these, but I do know I'm going from a slower velocity to a higher one. If it freaks you out that we have two lines like that, you could always connect them too if you wanted to, but you don't even necessarily have to do that. So then this part's actually a bonus on the test, but if you're watching these videos, you'll know how to do it. Since it says ignore any acceleration, think, well, I have no acceleration, I'm just going instantly from one velocity to another. So there's actually no acceleration, so you'd end up on the axis. You'd have 0 acceleration. You wouldn't have a positive, you wouldn't have a negative, it's nothing, no acceleration. All right, so for the calculation, this formula that we're going to use, since it's telling us to ignore any sort of acceleration, there's only one formula that ignores acceleration. Right? We could use our v equals d over t. There is another formula that would tell us our distance, or be able to tell us our time as well. In this case, we're looking for a total time, though. I think on the test I have you solving for a total distance or something like that, but both of these processes will be the same. So it looks like, to begin with, Sydney was walking at 2 meters a second for a certain amount of distance, and then she sees a friend, and so she ends up trying to catch up to her friend. So she goes a little bit faster, 3 meters a second to catch up, but that's for 16 meters. So that's in two parts here. So the first part of our travel, I've just labeled it part 1, P1 for part 1. We have a distance and a velocity. And then for part 2, that's a terrible P even for me, we have a distance and a velocity as well. So let's go ahead and look back up at what those are. 2 meters a second for 39 meters. 39 meters, 2 meters a second. And then for part 2, 16 meters at 3 meters per second. 3 meters a second, 16 meters. All right, so let's go ahead and figure out what our times are. All right, so for part 1, we can use the same formula, v equals d over t. I know my velocity, right? That is 2. Just putting my v right here. I know my distance was 39. So we can solve for our time. All right, let's go ahead and get rid of this fraction. So I'm going to multiply by time to get rid of that. Do the same thing to our other side here. So we're left with 2t equals 39. Kind of a poor choice of formatting here on my part. Trying to get t by itself here, let's go ahead and divide by 2 to get rid of that. And let's go ahead and do it to the other side here. So we're left with t equals whatever 39 over 2 is, which would be 19 and a half. All right, so think about what that 19 and a half means. We're dealing with time, so that's seconds. So we're calculating the total time that she's in motion for. Well, we know part of the time. The first part of our walk here took 19 and a half seconds. So part 2 of the walk, how long does that take? So I'll do my math up here for that. Again, kind of a really poor choice of formatting here on my part. What is going on with my marker? All right, v equals d over t. I know my velocity. I know my distance, right, 16. I don't know my time. Let's go ahead and figure that out. Get rid of the fraction, so multiply by t. Do it to the other side, like anything in algebra, and I'm left with 3t equals 16. I should have an answer kind of in my head already. Let's divide by 3 here to get t by itself. Do the same thing over here. 16 divided by 3. We have a time of 5.3 seconds. All right, so now I know part 1, that took 19 and a half seconds. Part 2, that takes 5.3. So what's my total time then? That's what I'm trying to figure out here. So my total time would just be, let's say t or t total, would end up being 19 and a half plus 5.3. Let's go old school. 5 and 3 is 8. 9 and 5, that's going to be 14. 24.8 seconds, my total time there. All right, so explain why the final answer is reasonable. Well, it's reasonable. That would be a positive because you can't have negative time, right? Negative time would mean backwards in time, so we can only have forwards in time, so that makes a whole lot of sense. Since it is time that we are dealing with, makes sense to have the unit in seconds. You know, when's the last time you had somebody say, oh, I'll be there in 24.8 meters, right? That wouldn't make a whole lot of sense, or 24.8 meters per second. Seconds would be the only thing that makes sense for our unit here, and it makes sense that we would take longer than 19 and a half, longer than 5.3, because that's only part of the trip, so together we'd have to add them up to get our final answer. All right, good luck on your test.